Good morning, good afternoon, good evening, hello. Let's see. Oh, yeah, continuing on. Acids and bases, equilibrium. But before we really get into equilibrium in detail for acids and bases, let's define a useful term called pH. So, all these slides, let me try to slant toward the idea of pH and what is pH. I'll define it in a second. By the way, strong acids have a very low pH. Um, Very weak acids have a pH close to 7 or a little bit below. 7 is a neutral pH. Weak acids, well, vinegar and lemons have pHs somewhere in the area of 2 and 3. On the other hand, strong acids have a pH of 1, 0. They can even go negative, believe it or not, because of the definition of pH. But by the time they go negative, it loses most of its utility. Here's another chart of weak acids. 10 to the negative 2 is a fairly strong weak acid. So this HSO4 ion in equilibrium, the acid and the conjugate base, that would have a fairly low pH all by itself. On the other hand, something like phenol with a benzene ring and an OH hanging off of it might dissociate a little bit into the phenoxy ion and the hydrogen ion. But still, that 10 to the negative 10, that's a small number, so the pH wouldn't be that low. Let's see. Oh, yeah. Just another list of common acids. Sulfuric acid's way cheap and inexpensive. Same for hydrochloric acid. Sulfuric acid, I think, is the most common chemical, the most often used chemical in industry and production these days. All right, let's get into more detail here. I'm going to skip this stuff. More weak acids. These weak acids, and I don't know they're weak unless they're not on the list of strong acids, which I've memorized. All these would have a low pH, but not as low as a strong acid. Oh yeah, what about the weak bases? Weak bases are so famous very, very often for having this nitrogen base. So there's a nitrogen in the middle, a lone pair hanging off of it. Sometimes phosphorus can do the same thing with its lone pair in the same family as nitrogen. But anyways, it doesn't really matter what this part is hanging off the other side of the nitrogen. Call it a ring, call it a chain or a branch or something, as long as that nitrogen, and this could appear anywhere in a larger molecule, a kind of a functional group that acts as a little bit of a base. So here's my nitrogen with its lone pair, and no matter what is hanging off the nitrogen, it can interact with the water to some degree, probably, and function as a somewhat of a base. Here are some constants for those. Let's see. 10 to the negative 5, kind of weak base. These are the Kb values for these. That's a stronger base. That's a stronger base. This one's on the level of this one. Same for this one. This is, oh, that, my goodness, that's 10 to the negative 9. That's a very weak base. But still, nitrogen, 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 nitrogen. Get the idea. I think I'm going to skip on by this. Would this have let's see, a pH of water is 7. Would this beaker of acid have a high pH? I mean, a pH close to 7 or a pH very far from 7? Well, I wonder how many of those acid molecules dissociated. There's one. One hydrogen came off from the, where is it? Oh, it's right there, duh. So these two dissociated. The other 9? 1, 2, 3, 4, 5, 6, yeah. The other 9, so 1 out of 10 dissociated. So, it wouldn't be a terribly low pH. Wouldn't be as low of a pH as a strong acid would be. Oh yeah, this goes with the previous picture. So let's see, so I have one of these in the numerator, one of these in the numerator, and 9 of these undissociated in the denominator. So the constant for that picture would be 0.11-ish, which is a fairly strong weak acid. But remember, the strong acids have constants in the thousands and millions, so other common acids, tummy juice, limes, lemons, sodas. Common bases, your blood's a little bit basic, egg whites, baking soda, coffee. Coffee's basic. Alright, here's the definition of pH. Well, not quite. Getting pretty close. In any mixture, in aqueous solution, there's this balance between H plus and OH minus. If I have a whole bunch of H plus, like up towards 1 molar, then theoretically I have almost no OH minus, or or very, very little OH minus. If I had a H plus concentration of, oh goodness, what would this be? I shouldn't say that. This is an H plus concentration here of 0.00000001 molar. It's called a pH of 7. This would be 0.00000001 molar, 0.00000001 molar. And it just keeps getting smaller and smaller. But on the other hand, the hydroxide ion concentration in that same solution, in that same beaker, would be growing larger. So if I have more of this, I have less of this, or if I have less of this, I have more of this. And the deal is the product of the two must be equal. So I take the hydrogen ion concentration times the hydroxide ion concentration. I call that Ka for the normal dissociation of water. So there's in water, there's my H plus, there's my OH minus. If this one's equal to this one, then it's sort of like x times x, and x squared equals 10 to the negative 14. So what that x must be equal to 10 to the negative 7. So that 7 right there is reflective of that pH of 7 right there. Although that's a little bit unclear still. This says in pure water at 25 degrees. If the water warms up, the particles move faster, they collide more frequently, and actually this dissociation is a little bit larger than 0.00000001 molar. Maybe it's 0.00000011 something molar. And the warmer it gets, usually the larger this constant grows. Or I could say the greater the degree of dissociation or autoionization. This is important to know. The product of these two molar concentrations must be 10 to the negative 14 at room temperature. And that goes for not only a water solution, but any acid or base solution. So that's very, very useful. But there's an adjustment that we can do. Alright, anyways, let me show you this first. Here's the definition of pH. pH is a mathematical operation to make it work a little bit easier. These numbers, these hydrogen ion concentrations are often so small, we take the negative logarithm, take the negative log of that small number to get a more reasonable number. The pH scale goes from about 0 up to about 14 or so. Similarly, we have something called the pOH, which most folks haven't heard about, but it's an equally as useful scale. And in other words, this one and this one go hand in hand, the pH and the pOH. The pH plus the pOH value has to equal 14, or just like we said above, the product of those small concentrations needs to be 1 times 10 to the negative 14. This is interesting, but a little confusing. So we better try a few. Oh, for future reference, there's an analogy to this, an extension, for any acid conjugate base pair. For future reference, for any Ka and any Kb for an acid and its conjugate base, the product must still be 10 to the negative 14. Or in other words, the negative log of the Ka value plus the negative log of the Kb value for any one acid-base pair. Now, I don't mean to scare you or confuse you with this right now, but I'm just saying we're going to see this again, and it's very comparable to, analogous to what we do for water, the H plus and the OH minus in the aqueous solution. Alright, so we'll revisit that maybe later, definitely later, but definitely not now, but I had to show it to you. Alright, here's the pH scale again, different way to look at it. pH is 7, neutral in the middle. Anything lower than 7 is an acid, anything higher than 7 is a base. And here's my acid concentration, 1 molar, 0.1 molar, 0.01 molar, 0.001 molar, 0.0001 molar, 0.00001 molar, 0.00001 molar, and by the time you're here, it's 10 to the negative 7 molar, which is sort of the measured autoionization dissociation for water anyway. So this is 0.000001 molar acid, but it's also 0.000001 molar base. By the time we're over to here, we have 1 molar base, 0.01 molar base, 0.001 molar base, 0.0001 molar base. You get the idea. As this one gets larger, then this one will get smaller. This would basically be, let's see, that's to the 0. I'm confusing myself. I'm trying to figure out in my head what the hydroxide ion concentration would be over here. This is, well, let me go on. Here's a fun table. You can play with this in your spare time if you like. If I was told the pH, what I do is I take the opposite of the logarithm function, so to go backwards. Oh, did I list this above? Yeah, right there. To go backwards, get rid of the logarithm function. You go 10 to the x power. Like if you forget your logarithm functions, if you look at the logarithm button on the calculator, and the reverse function right above that usually is 10 to the x. Excuse me. So as I was saying, if I was told the pH, I just take 10 to the negative pH to go backwards and find the hydrogen ion concentration. If I were told here the hydrogen ion concentration, oh my bad, that's hydroxide ion. If I was told the hydrogen ion concentration, I could take this number. Let's see, the negative logarithm of this number gave me 8.43, and like I said down here, Kw, which is 10 to the negative 14, divided by the hydrogen ion concentration. So this one divided into this one gives me this one. I'll let you figure out the rest of that table if you're so motivated. I'll put a PDF of this online, of course. You can go play with it a little bit. I think it came from a different textbook, so it's good practice in the beginning. Oh yeah, so anything with a pH lower than 7 is an acid, higher than 7 is a base. Here's another way to look at it. The pH plus the POH. What's 12 plus 2? What's 11 plus 3? What's 10 plus 4? What's 9 plus 5? What's 8 plus 6? What's 7 plus 7? Oh yeah, it's 14. Let's try that table again. Or here, another way to summarize it. Here I had my hydrogen ion concentration given. The negative log of that number gives me my pH. There's two ways to do the POH. You can just straight up divide Kw by H plus to get the the OH minus concentration. But the way I do it is, sometimes I'll take the pH, subtract it from 14, then take 10 to the negative that term. Here it's 11.54. 10 to the negative 11.54 gives me this number. Maybe you think that's a little bit longer of a route, but usually in my experience it ends up confusing me less. So lower than 7 acidic, higher than 7 basic. Take a look at those notes sometime. Try some on your own. Just another listing of some common acids and bases. What do weak bases do? Oh yeah, weak bases dissociate. Weak bases dissociate water interacting with the water. Weak bases interact with the water and yes, in equilibrium with the water to make the OH minus. The negativity on the weak base, maybe it's a lone pair only, or maybe it has a negativity to it as well. But that negativity attracts a positivity of the H plus, creating the conjugate acid and the OH minus in water. The larger the Kb value for a base, let's see if I can zoom in on that a little bit. The larger the Kb value, 10 to the negative 4 is fairly large for a base dissociation constant. Let's see, that would make the pH fairly high, quite a bit higher than 7. On the other hand, 10 to the negative 7 Kb is, oh my goodness, that's pretty weak base. That would be very, very close to 7 actually. Yeah. The closer to 7, the weaker your acid, the weaker your base, and the closer to this pH of 7 it is, the more difficult and precarious the calculation ends up being. Did you guys know that antacids were really antacids? So like Tums and Rolaids, Pepto-Bismol often do the same. They cancel the acidity of the bases. I think I better stop there. Thanks guys. See you in class. I need another video soon about some more details on the pH scale and some mixtures of acids and bases for calculation.